Hello and good afternoon to everybody. So it's a very big pleasure to welcome you to our second lecture within this series, public lecture series of this European project, which is called Strong 2020. I am Catalina Curcianu, and right now I am in the Frascati laboratories of the INFN. By the way, I thank to the staff of the INFN Educational Service for providing all the support for organizing these lectures. Thank you, Susanna. Thank you, Deborah. Thank you, Elisa. And I'm the coordinator of the dissemination and communication activities within this European project. And for those who were here with us in the first lecture, you might know already. For the others, I'm just telling you now that our project, Strong 2020, you can find more information on our website. You can see it written here. So just please go and have a look of what we are doing. There are also some information for public. The project, it's a big project, started June 2019, and it deals with studies of the strong interaction. So strong interaction at frontier of knowledge, it's fundamental research, but also applications. And this project has received funding from European Union's Horizon 2020 Research and Innovation Program. As I told you, it's a very big project, which involves about 3,000 researchers from 36 countries. Out of them, 14 are European member states, and the others are belonging to institutions coming from countries which are outside Europe. And we have a lot of activities which is experimental. We are developing new types of detectors, new type of experiment and experimental techniques. We are also performing theoretical research, but we are also hosting researchers in our main facilities, which in Europe are the ones which are machine accelerating machines from COSI in Germany, MAMI in Germany, Frascati Laboratories in Italy, where I'm right now, ELSA and GSI Fair again in Germany, and the well-known CERN, to which you will hear more from our speaker of today, Laura Fabbietti. And this allows me to introduce Laura. Laura is a researcher, young researcher, who is leading a team of researchers doing very fascinating research at LHC. She will tell you about this more, which has an impact, a very broad impact, which goes from particle physics and nuclear physics and hits high in the sky to understanding better the neutron stars. This is, as I was telling you in the beginning, the second lecture. For those who are interested in the same website where you are looking at this lecture right now, you can also find, just go back and look more, you can find the very first lecture, which has been the kickoff in December, related again with an item connected with nuclear and strong interaction. How big is the proton? And with this, just not to make it much longer, I welcome Laura to our series, and I leave the floor to her to tell us about the strong interaction and the renaissance of nuclear physics at Large Hadron Collider. Thank you, Laura, for accepting our invitation.
Hi, Caterina. Nice to meet you live, and thanks a lot for the invitation. It's the first time that I am live on some kind of platform. I hope I don't screw everything up. So as Caterina said, so today I will show you a little bit of a renaissance of nuclear physics at the Large Hadron Collider, LHC. I'm Laura Fabbietti. I work in Germany at the Technische Universität München. And there I have a group that study nuclear physics, actually an extension of nuclear physics, because we do not look only at neutrons and protons, but also at other hadrons with strange quarks inside. And in the next 30 minutes, you will see why these hadrons with strange quarks are relevant. And in case you have time, I would like to invite you to look at this little movie cartoon we produced at the TUM to explain the Iperon puzzle in neutron stars. Indeed, this renaissance of nuclear physics at the LHC has a very nice connection to the physics of neutron star, and I'm going to talk about that today. So here's the outline of what you are going to learn in the next, let's say, during this talk. I will obviously start providing some information about neutron stars, so the identity card of neutron stars, which kind of objects they are and why are they interesting at all. And then I will tell you how we can study the content of objects which are far away in the sky here on Earth in a laboratory. I will explain you what an equation of state it is in general and what is an equation of state for neutron stars and which kind of role it plays. And we will see that in order to understand this equation of state, it is very important to study interactions among particles that might be or not be inside neutron stars. I will show you what these experiments at the LHC, the Large Hadron Collider, have to do in common with neutron stars. And finally, I will show you how far we are today really in the understanding of these objects and what the future might bring us. So first of all, one can ask, how do you create neutron stars? Where do they come from? They are originated from supernova explosions. And supernova explosion, they have let's say, a path starting from normal star that must be massive enough to lead to supernova explosion. But first, you start with the burning of hydrogen into helium. And then you burn until there is no helium left. And what happens if you burn material inside the star is that the pressure going outwards, which sustains the objects, will become smaller because you have less material. And the gravitational pressure induces some pressure from outside to the inside. And then this means that the object will become hotter. And then you will start to produce heavier elements, up to iron. When the central part of your object is constituted mainly only out of iron, then if mass is big enough, what happens is that eventually you might have a supernova explosion. And you can see in this extremely colorful plot that depending on the mass of your initial system, you can, if you look at now the second line from above, you can have eventually a supernova explosion and then a neutron star. Neutron star is basically a relic, and somehow why should be these relics more important than any other stars that we know? Well, the thing is that what is very peculiar about neutron star is that they have a very small radius between 10 and 15 kilometers, but they have an extremely large mass. So in the order of 1.5, even 2 solar masses. Now, if you think about the Earth has the mass of the Earth is 3 parts per million, so smaller than the mass of the Sun, and the radius of the Earth is more than 6,000 kilometers. So if you compare these numbers, you can see that the density of a neutron star is really several orders of magnitude larger than the density that we have normally for atoms, okay? So there are large density for these objects that are called neutron stars. We know that the crust of this object is composed of neutrons, that there are electrons on the surface. Well, we know that because these objects, they rotate very fast, and if you think about your bike, and the dynamo of your bike, how you produce electricity when it's night and you want to see something around. So then you have a parallel for neutron star by rotating this. So basically electrons which are rotating produce a kind of a dynamo effect, and they emit radio frequencies. And these radio frequencies can be observed. And so we know something about neutron stars. We actually know the mass and the radius, but we do not know what is inside because the density is so high that several hypotheses can be, let's say, put forward about the content. And so one of the questions in nuclear physics, so which is the topic I normally am interested in, is which kind of matter is inside neutron stars? Okay, first I want to tell you how we can measure some properties of neutron stars. That's not really us, meaning not physicists who work at the LHC, who measure the property of neutron stars. This is astronomers, but I'm going to show you how to measure the mass of neutron stars that can be measured extremely precisely, and how to measure the radius of neutron star, which is a little bit more difficult as a measurement, but still carried out. So the best measurement I am very sorry, the best measurement for the neutron stars is a method called Shapiro delay. Basically, you need not only a neutron star, but you need a companion. And this companion here is the bigger star you see on the left-hand side. And these two stars, they rotate, okay? And by rotating, and then if you think that your neutron star emits radio frequency, clearly, when the radio frequency that are emitted towards the observer, you see here this little arrow shows you the Earth, the place where you are, and you can measure this signal coming from neutron stars. The signal will be disturbed if it crosses the companion by chance, because by the rotation, the signal is, let's say, going through the companion or very close to it, or if a companion is far away while the signal is transmitted to us. So basically, this is something which is basically due to general relativity, because the gravitational field of a companion modifies the path of the electromagnetic wave that you are going to detect. And this is called Shapiro delay, meaning that basically if the light, let's say, or the photons that you want to detect on the Earth have to pass by, close by a very heavy system, they will make, let's say, they will go through a longer path, will be deviated. Okay, so it is possible to measure these deviations, and actually what you will measure is a delay, because of the deviation, when you go and you buy bread, if you go straight to the shop, or if you make, let's say, a deviation to get a coffee, obviously you will arrive at the shop later. And this is exactly what is measured, a deviation in time, so a delay. And the delay is shown here in this plot on the left-hand side by this peak, right? If you would have no deviation, the curve will be flat, but this peak, after some time, on the x-axis you have the time that you spend looking at the measurement, you have a peak. And this deviation allows you to measure very, very precisely the mass of a neutron star. So in this specific, let's say, discovery of a very high, massive neutron star done in 2010, and published in the renowned Nature journal, the mass of a neutron star was, back in the days, the most massive neutron star found, which it was 2 times the sun. So it was as heavy as 2 times the sun. And the error, if you look at this number, the mass is 1.97 plus minus 0.04 solar masses. You see that the error is really of the order of a few percent. So what you have to take home is that masses, so neutron star has very high masses, and those masses can be measured with high precision. For radii, things are much more complicated. And again, in order to measure radii, you need a companion. So, and basically you need a little bit of cannibalism thing. So basically the neutron star is basically sucking material from a companion. The companion gets thinner. The neutron star has a so-called accretion disk around itself. And this accretion disk, this material, which is eaten from the companion, will create excitations, will be exciting, will emit X-rays. And these X-rays can be measured. And clearly, the larger the star, the larger will be accretion disk. And this will influence the X-ray spectrum. So by measuring X-ray spectrum, one can measure the radius. And so the normal companion from which the cannibalism of getting the material happens is a white dwarf. And here you can see a representation of a white dwarf on the left-hand side, and then a neutron stars on the left-hand side. On the right-hand side, you see the neutron star is really super small, has a small radius, but it has a huge accretion disk. And from this accretion disk, you will emit X-rays, and you can measure them on the Earth. Now, the flux measured for this X-ray emission is proportional to both the mass and the square of the radius. And somehow you already see here that, okay, this formula is complicated. It contains two variables. And what in the end happens is that the measurement of the radius has a precision of only 25%. So it's not few percent, 1 or 2% like for the mass, but it's, let's say, a measurement so far that is hampered by very large error. Okay, but still, one can measure mass and radius. And now, these two measurements, its two variables, are extremely important to be connected to physics that we do at the accelerator and to what we can learn at the accelerator. Without these two measurements, we do not have any reference whether what we are making, what we are hypothesizing about the content of neutron stars is correct or not. So now, as I told you, you can measure the mass and the radius. And now this plot shows you on the y-axis the mass, on the x-axis the radius, and collect the information which I told you so far. The mass can be measured very precisely. You see this line, this yellowy line is very thin. If you look at the projection along the y-axis. Well, the measurement of the radius is very broad, right? And sometimes they are correlated, but for the mass measurement, for example, only the mass is measured alone, so without the radius. Now, how can we, obviously, for each measurement, we will have one line or one point. And now, what can we do with this astronomy measurement? So what we want to do, so physicists who are nuclear physicists, we want to find the unique recipe for neutron stars. So when you cook, what do? You normally have a list of ingredients and then a way how to combine these ingredients to obtain your favorite dish. The same thing we want to do for neutron stars, and we would like, first of all, to understand which are the ingredients, right? And then there are several hypotheses that one can do about the content of neutron star and hence its ingredients. The first, maybe more plausible hypothesis is that there are only neutrons inside neutron star, that exactly like on the crust, also in the inside, you have plenty of neutrons. Neutrons are actually not elementary particles, but they are composed by quarks. So you can see on the left-hand side, you have circles with two green dots and one red dot. The green dots are down quarks, and the red dots are up quarks. There are 6 kinds of quarks, and up and down quarks are the lightest quarks that we know, and neutrons and protons are composed only by these 3 quarks. By 3 quarks, taking a different choices of down and up quark. So the first hypothesis is only neutrons in neutron stars. Clearly, these neutrons will be clearly packed together. So, but there are neutrons. Another idea is that maybe you do not have neutrons in neutron stars. You just have quarks which are free to move around. So you do not have these little bags which contains 3 quarks each. But these bags are broken. It's a little bit like when you have, like say, container, plastic container with some milk, and then the container, it's cut, and all the milk is spread around, and then the milk will assume the shape of a new container. Either on the floor, it will completely dissipate, but inside the neutron star, gravitational pressure will keep the milk inside a finite volume, but obviously you do not have, so the milk can flow around. Little bit similar, you can imagine these quarks, these quasi-free quarks that go around. So these are 2 possibilities. This possibility we are investigating now at the LHC is slightly different, and it's actually only a bit different than the neutron-only hypothesis. Exactly as you form a neutron, you can also form an hyperon. And what do you have to do to form an hyperon? You replace one of the 2 up or down quark with a strange quark. So you see in this new picture that appear that you don't have 2 green and 1 red, but you have 1 green, 1 red, and 1 yellow. And yellow are the strange quark. So the hypothesis that is currently studied is whether maybe we just move one step forward with respect to neutron-only star, and we have Iperon stars. So we have inside neutrons a mixture of neutrons, but also some Iperons, meaning that the neutron star is accommodating also strange quarks and not only U and D quarks. Now, so making the hypothesis about the ingredients is one thing, but in order to have a recipe, one needs to know how to combine, right, the ingredient, what to cook when, and when to add ingredients. This in particle physics goes under the name of interactions. So the interaction among the neutrons or the hyperon and the neutron inside the neutron stars is what drives the recipe of neutron stars. Actually, we can call this interactive system in the language of mathematics as in another way. And then we talk about equation of state. So what is the equation of state? This is nothing else than the response to pressure of the system. I make you a very easy example. If you take a pillow and you try to compress it, so you apply pressure, okay, this pillow will compress, okay? Then you will say that the equation of state of the pillow is soft. If you take a wood box, a wooden box, this is different. If you try to compress it with your hands, you will not achieve much because the response of the system to the external pressure, it's, let's say, harder. And then you will say that you have a stiff equation of state. So a stiff equation of state means that you have a steep pressure variation when you try to increase the energy density. So when you try to compress, the answer, let's say, of the system will be an high pressure towards the outside. So now, why can we have, now let's keep in mind this equation of state at the side, and let's know that this tells us the response of the system. Before we go to the connection between the equation of state and the property of neutron stars, now I want to explain to you why Iperons, okay, which are the heavier, as you can see here on the scale, cosines of neutron, can appear in neutron star. The scale already tells you that it's more expensive to produce Iperon, because when you have a particle which is heavier, it's like when you have a spose who eats a lot. This spose is more expensive to maintain than a person that does not eat so much, right? So same things for particles. If the Iperon is heavier, nature will not produce it very willingly because heavier particles are more expensive. So why can those Iperon appear at all? So this has to do with some energy consideration that Fermi made many years ago. And the thing that neutrons are fermions, and they do not like to sit on the same energy level. They are individualists. So meaning that the energy level of neutrons and their quantum numbers will increase, okay, if you have many of them. You cannot pile them, you have to pile them up, okay? And if you pile them up, what you will do is that the energy of the system will grow and grow and grow. And at some point, what happens is that although the Iperons, which are much more massive than the neutrons and hence more expensive, are not the first choice for the system, at some point, what happens is that the energy on the left-hand side is so high that neutron disappears, Iperons appears, and the energy of both systems decrease. And so for nature, it becomes eventually more convenient to create heavier degree of freedom. This is the way it's called. When you have new particle, you say you have new degree of freedom. Then having the old, too many of the old pile up together. Think about like when you have a society, a club, with a lot of members of a certain age, and then you continue to acquire members of a certain age. At some point, you might feel the need to renovate a little bit the atmosphere and acquire members who are younger, maybe more dynamical, and have even less requirements, right? Same things happen within the neutron star. At some point, new degree of freedom are accepted into the club. So this is an hypothesis which is, let's say, rather, let's say, plausible, because nature is greedy. Nature always tries to save money, and save energy. Hence, the idea is that Iperons can appear in neutron stars. But then why shouldn't I bother in investigating the interaction? Because there is a point. There is a point which is completely unsolved, which deals with the interaction of Iperons and nucleons. So we have clarified what the equation of state is. Now, why is the equation of state important for neutron stars? So in mathematics, we have a tool, let's say, that is the fact that we know the formula which guarantees that the neutron star is stable. Okay, so it's formed and will not collapse into a black hole, will not explode, is stable. And this mathematical formula comes basically from general relativity. And these formulas are very well known. Now, imagine that you have some hypotheses about the neutron stars. Imagine you have only neutrons inside the neutron stars. Since you know the interaction among neutrons, you can also draw a plot like this plot on the left-hand side, energy versus density. This line, it's an equation of state. And this equation of state is rather stiff. It tells you that if you have neutrons inside the neutron stars and you try to compress the system, right? So you go along the x-axis and you have more and more density, your energy will also rise, right? And it rises rather fast. The fastest you rise, the steeper is the equation of state. Now, these mathematical formula coming from general relativity are super cool because they allow you to map univocally, meaning one-to-one, the green line on the left-hand side into the green line on the right-hand side. That tells you the relationship between the mass and the radius of the neutron stars. So this is now the way you use all the information I provided to you today. So you have on the one hand side an equation of state that you can measure in a laboratory for nuclear physics for some objects that might be contained in the neutron stars. And on the right, and these translate one-to-one into a line on the mass versus radius plot. And there, astronomers can make points. And it's clear that your line must go through the measurements, otherwise this line is not correct. Now, what happened now here if we introduce Iperons, right? Now you have seen in the animation, this magenta ball appeared. So you have a lot of Iperons. I just told you that this is energetically favorable. Because nature wants to save money. But then what happened to the equation of state is that in general, it is expected that the equation of state will be a little bit more slow. It will become softer. This is a normal reaction of nature. Nature is greedy. She wants to save money. So she gets cheaper partner into the neutron stars. But this relaxes the system. The pressure is going down because, you know, in the club, people feel more at ease. There are less competition among the older members and the pressures go down. And this makes the equation of state softer. Okay, so far so good. We all like a little bit of a more, let's say, relaxed environment. So what's the problem? Well, the problem is how these map into the mass and radius of the neutron stars, because what happened to the mass and radius curve is that this also goes down. So the maximal mass that a neutron star can achieve, it becomes smaller, meaning that too soft equation state, it's a little bit problematic because you would not get with your orange curve on the right hand side, you would not get through this horizontal yellow bar, which is your observation from astronomy. So this is the Iperon star puzzle. Iperon should be in, okay? But if equation state is too soft, then we are completely in trouble because the masses of neutron stars can be very heavy. And if equation of state does not match this measurement, we have a problem. So there is only one way out. So maybe Iperons are in neutron stars or not. The only way to find this out is to study the interactions, because the interaction of the Iperons with the neutrons or with the protons is what characterizes the equation of state. The theoretician, in order to draw this line, needs to know about the interaction. So how can we study the interaction from an experimental point of view? Well, we are to go in a place where you have a lot of these particles, where you have a lot of protons and also a lot of hyperons, and you produce a lot of them, and you can study then their interaction. And this place is the Large Hadron Collider. This is the largest and fastest accelerator in the world. And this photo from the sky shows you the LHC ring in Geneva. This ring goes through Switzerland and France, is 27 kilometers long. And there, the advantage is that you collide two protons. So you start off only with two protons, but the energy is so large at which you can collide these two protons that you produce at least 20-30 particles after the collision. Actually, when you collide two lead ions, you produce even 10,000 particles after a collision. But if you collide only two protons, right, you produce 20-30 particles. Among these particles, as you can see here on the right-hand plot, you can look at pairs that you are interested in. So we say that we want to know about the Iperon interactions. Iperons is everything which contains at least one strange quark. You remember? There are several of them. But here in this plot, you have an example of most exotic of the Iperons. So this is here this sphere with three red quarks, which are three strange quarks. This is the omega Iperon. And then on the left-hand side, you have a proton, where you have two U quark and one D quark. And basically, this image shows you how this interaction study is done. You look at pairs for which you want to know the interactions, which is necessary to calculate the equation of state. And then you want really to extract this glitter red dialogue between these two particles. And this seems complicated because it seems like intercepting the discussion of two people who are talking when leaving a party and going home together. And this is obviously not so, let's say, straightforward how we do it, but there is a mathematical observable which allow us to do this. So in this mathematical observable, first of all, needs for us to measure the velocity of each of these particles. So the Alice experiment allow to measure the velocity of a particle extremely precisely, and also to know which particle, the particle name. So with Alice, it's very easy to know whether a particle is a proton or is an Iperon. And I will show you a little movie that shows you the heart of the Alice detector, the TPC, time projection chamber. This is this red volume. And now when you have a collision, you will see that particles will be flying around. And actually, this detector that is actually full of gas is able to reconstruct each of these particles. So this trajectory that you see now in the movie is, it has some bending in a magnetic field. And the bending of this trajectory, which can really see as if we have a 3D camera that really can look into particle, allow us to calculate the velocity of a particle and also to know which particle it is. So for us, it's possible even to do this when particles decay, because the detector is so powerful that even the decay can be reconstructed and then the particle can be assigned their real name. So as you can see, it's really like having a 3D camera. And this 3D camera works extremely well for, it has basically, as you see there, written 200 frames per second. It's like really like a 500 megapixel 3D camera. At the moment, we even plan, starting from 2022, to acquire photos with a velocity which is 100 times higher than what we do today. Okay, but what we do today was enough to study the interaction. And now, so we want to know how this interaction can be really studied. Okay, you see again on the left-hand side this cartoon of the reaction. So this is a typical proton-proton collision at 13 TeV, tera electron volt. And you can see that many particles are produced, but you are interested only in certain pairs. Okay, you will pick up the pairs. you will measure the momentum of a pair, meaning the velocity of a pair. And you not only the velocity in absolute value, but you will also see in which direction the particle goes. And now what you have to do is just to determine whether the particle from when traveling from the interaction to your detector tend to go more close to each other. Okay, so if the momenta, which are vectors, tend to align, in this case, it means that you will have an attractive interaction. In the case that the two momenta vector diverge, right, it means that you are encountering a repulsive interaction. If you want to take the same example, so the two people going out from a party and going home, if they like each other, they will continue walking side by side, eventually coming closer to each other. If they don't like each other, they will speak for a couple of minutes and then everybody will go his own or her own way. The same things happen to particles. So we measure the momenta, we measure the so-called relative momenta, and we can build a mathematical observable, which is called correlation function. And the correlation function, which will tell us exactly whether we have attractive or repulsive interaction. And this information then can be used to formulate an equation of state. And the equation of state then tells us which masses and radii are possible for neutron stars. Now, I want to show you at least two plots that are real plots that we measure and publish within ALICE at the LHC. And here you can see the correlation measure between a proton and a lambda Iperon. A lambda is the simplest and also lightest of the Iperons. It has only one quark, which is different from the proton. So it has only one strange quark, so more. And this is a typical correlation function that we measure. So this plot on the y-axis, it has the strength of the correlation function. On the x-axis, it has a variable which is called k star, which is the relative momentum. And this correlation function is very easy to interpret. If it would be flat and equal to 1, it would mean that the two particles that you are looking here, they do not interact. Because when the correlation is 1, it means that no interaction was taking place. If you look now at the y-axis, you see that this correlation, okay, it's not a constant, it varies at the function of the variable k stars, but it reaches values up to 2, right? Meaning that the interaction is there. And what we also know is that if the interaction is larger than 1, then it means that the interaction is attractive. If the interaction is lower than 1, then it means that the interaction is repulsive. So if you look now at this plot, without being an expert, you can see that for most of the time, the correlation function is larger than 1, meaning that the interaction is mostly attractive. But there are some regions, if you look at the inlet, where the correlation function goes a little bit below 1. This means that some part of the interaction will be repulsive. Actually, what this really means is that if you take a proton and a lambda, they will attract each other until they come too close. And when they come too close, they will not want to be really all the time on the top of each other. So we speak about a repulsive core of the interaction. It's like when you have two people who like each other very much, but they don't want to live together, right? They like to meet, to go for the beer, but they really don't want to live together and stay together all the time. Same thing about proton lambda. So actually, as I said, lambda is actually only one kind of Iperon. There are many. So actually, they all have names they are all named with capital Greek letter. And the difference between these different Iperons are quantum numbers, and also how many strange quarks, I mean, you have inside. For example, we said that lambda has only one strange quark. Sigma has also only one strange quark, but it's different than lambda because of some quantum numbers, which are not exactly the same, like for the lambda. And Xi, for example, has two strange quarks. So there are many Iperons, and different kind of Iperons can be inside neutron stars. So as you can see in this plot, you do not have only neutrons and lambda, but you could have sigma and also Xi inside neutron stars. So meaning that your job is to measure all interactions, not only proton lambda, but also measuring proton sigma, proton Xi, and also other. So this is why we do not have only one plot, right? But we have here different plots. So you can see that we have different plots. Each plot corresponds to one measurement and to one results which was achieved. The correlation functions have different shapes and also different height because the interactions of the pairs that you are looking in each plot are different. Many of the interactions have been measured already, and I want to show you another example, which is not so connected to the physics of neutron stars, but is also super interesting. So in this initial sketch of the collision at LHC and the production of a nuclear of the hadrons of the particles of interest, I show you at the beginning the example of the proton with the most exotic of Iperons, which is the omega Iperons, which contain 3 strange quarks. This is the heaviest and also more difficult to produce. And the interaction between a proton and an omega was never measured before, but it was measured last year and also published in 2020. And this is the correlation function. And correlation function, the strength of the correlation function tells you about the interaction. This is plotted as a function of the relative momentum, as we have learned. And now you are expert on correlation function, and you know that if no interaction would be there, then the correlation function will be 1, right? So you can see, you look at the plot, this is not 1, it's 7, 3, 2, so okay, there is some attractive interaction. But proton and omega minus are charged. Proton is positively charged, omega minus is negatively charged, so meaning that for sure there is electromagnetic interactions, right, which is attractive. But then there is also another interaction. I mean, the interaction we are talking all the time here, it's not the electromagnetic interaction, it's actually the strong interaction. It's the interaction that keeps quarks bound together. And this does not depend from the electric charge. And this is now demonstrated in this plot because the green line, very tiny green line, shows you how the correlation would look like if only the electromagnetic interaction would act between the proton and omega minus. But you can see that the data are different from this green line because there is this additional attractive strong interaction that bound together the quarks of one proton and the quarks of omega. Even if they are confined, these quarks, they still speak to each other through a strong residual interaction, and then this residual interaction is here seen for the first time. And I'm showing you this because these interactions are very difficult to calculate, and there are calculations which are called lattice calculations, which are done basically on supercomputers, where one starts from quarks and one want to try to reproduce this complex interaction of bound quark system. And we were able for the first time to compare the data to different set of lattice calculations. And actually the data are more precise at the moment than the lattice calculations, but still now this data can be used to test further lattice calculation to understand really this strong interaction in detail. And it's a pleasure because these results was published for the first time actually for Valley's collaboration in a Nature journal. They choose another. They didn't choose the photo we sent them, but we choose this beautiful mapping metastasis petals plot in pink and yellow, which I also like very much. But still, we were mentioned on the cover, which is for us an extremely nice thing to have. Okay, so now we have many interactions. So these are actually the most important pieces of this Iperon puzzle in neutron stars. Each piece is an interaction that should be measured. And you can see that there are green pieces and red pieces. The green pieces are the pieces which were known even before Alice started to develop this new method of correlations. The red pieces were the one which were not known at all. How it is the status today? We were able, if you go between these two slides, you see that some of the pieces, they change color. Some of the red pieces now are green. And for each green pieces, you have also a plot, which tells you that interaction now is known. But some of the pieces, they remain red. And actually, if you look inside these red pieces, you can find 3 particles. You don't have 2 anymore, but you have 3 particles. Because unfortunately, in neutron stars, since you have many neutrons, you cannot only look at 2 particles interaction and know exactly the equation of state. You also need the 3-particle interaction. Now the question is, okay, if you need 3-particle interaction, do you need also 4, 5, 6-particle interaction? Well, theoretically, yes, but practically, no. I mean, after 4 particle, we might have everything we need, because the strong interaction is actually short range. It means that each particle only talks to its next neighbor, and it doesn't care to the next to next neighbor. So they just really talk to the particle which lives in their front door apartment, meaning that 2 is not enough. 3 is very challenging. I think we can measure that. And once we will be done with 3, maybe we can even achieve 4, and then we will be done. So we will use these interactions. We measure the correlation at the LHC, as I showed to you, and then we have the interaction between 2 particles, and in the future also among 3 particles. This will allow us to draw an equation of state. And from the equation of state, we can go to the mass and radius diagram, and then we can see whether different hypotheses, for example, with Iperon, are true or not. If they are true, they will match mass and radius measurement. If they are not true, they will not match. And another important thing is that in the next year, we will have more and more data coming from gravitational waves, and these gravitational waves also draw boxes on this mass versus radius diagram, meaning that we will be able to test our equation of states based on the interaction measured in the LHC, not only against measurement of mass by a Shapiro delay technique or radii via X-ray emissions, but also against the measurement of gravitational wave. So I would like to thank you very much for your attention. I hope I could convince you that the topic is interesting, the measurements are extremely promising, and that there is a renaissance of nuclear physics at the LHC with a great opportunity to also understand the physics of neutron stars. Thank you very much.
Thank you very much, Laura. Thank you for being with us and giving us this overview of the activities you are doing to understand the interactions between strange carriers and the other part of the nuclear physics with this extremely interesting and fascinating impact on the neutron stars. And you received greetings from Krakow, by the way, in the chat.
Yes.
I remind you that if there is anyone who wants to ask a question, just please write it down there in the comments. Meanwhile, I want to ask you, Laura, so this is a type of research you are doing at LHC. And can you also tell us something about other types of research? So what else is being done in Alice?
I mean, in Alice, or you mean in the field? What else Alice is doing? So
yes, what else Alice is doing?
Actually, Alice is not an experiment designed to study interactions. So the main, let's say, scope of Alice detector is to identify the characteristic of the so-called quark gluon plasma. I was showing you that even for neutron star, there is the hypothesis that inside the neutron star, you just have an ensemble of quarks almost free, because quarks are never really free when they are together. And this is the scope, one of the scope actually of the ALICE detector. You collide two heavy nuclei, lead, you create this quark gluon plasma. This has been actually verified and demonstrated. And then you can study the interactions by looking, for example, at how the particles that are produced later on are emitted, how many particles are emitted, and how different particle species, how many different particle species are emitted. You can compare this, for example, to thermodynamic models, to hydrodynamic models, and you learn about the temperature of a quark gluon plasma, about the density, maximal density. You learn even about the viscosity of a quark gluon plasma, and you can compare to models like ADS CFT. Imagine that. So this is the bulk of the activities. But then another topics which is extremely interesting at LHC and is done with ALICE is production of nuclei and antimatter, because obviously we don't have so many antinuclei on our Earth. Actually, in a natural form, none of them. We have positrons, but antiparticles are not so abundant, right? And the LHC can produce them because the energy is enough to produce as much matter as antimatter. So, meaning that in general at the LHC, you can study these symmetries, the symmetry properties, for example. So, matter, antimatter, abundances, you measure masses. But what you can also do, you can also study properties of antinuclei, how they are formed, how much they are absorbed, for example. And this is also connected to a very important physics question, astrophysics question, which is, for example, indirect search of dark matter, because some idea are around that dark matter could convert into antinuclei, and people working on satellite experiments and balloon experiments try to catch those antinuclei. But if you do not know the properties at the accelerators, clearly all the future, most probably, observation will not clean, you know. So the accelerators, they serve to find new physics, maybe, so as envisaged, right? But they also serve to understand standard model particles, because all this standard model physics, nuclear physics, is necessary for many astrophysics topics, because otherwise observation will be only qualitative. So I hope this answers a bit your question.
Yes, thank you very much, Laura. This was very inspiring. By the way, you received some thanks for people and also a question from Randolph, who was our first speaker. And the question is, if you might know the answer, I would not know what to answer. How many unknowns are involved in the equation of states somehow, in the flux mass radius equation?
Yeah. So, I mean, normally what I showed you as a line in this equation of state is in reality a huge band. And if you take, for example, of the equation of state only with nucleons, with neutrons only, in a small percentage of protons, the problem is that everything we know from the theory comes from nuclei, basically nuclear spectroscopy. And there you can pin down, so you can test assumption about 2-body and 3-body interactions up to actually fourth order in precision, but only in the vacuum at rather large distances between these two nucleons. When you want to calculate the equation of state for large density, meaning that you compress the nucleon together, you don't know exactly how to extrapolate. So that's why normally these equation of state are very large. Now, what we hope at the LHC in PP collision is that since we create really sources of particles which are super tiny, they have the particles are produced at 1 Fermi distance. You have to consider that 1 proton has a radius, as you know, 0.8 something Fermi. So we produce them almost overlapping. So we think that with our method, we can maybe test really short range interaction, which also mimic high density. Obviously, you cannot really mimic high density because you don't have like 10 to the 5 nucleons, but at least you can test short range, 2-body, 3-body, and 4-body interactions in the next 10 years. And this, I really think that the LHC is the best place to do that. 0.84, right. 88 was the, I did it on purpose. Okay. I hope I could answer your question. So errors are huge. So, and for
there is another question, Laura. Another question from Helena Santos.
Yeah.
Who's saying, you have seen it. Neutron stars are cold, highly compressed matter, but collisions at LHC produce hot compressed matter.
Yeah.
How that is?
Okay, this is a very good question. So these interaction that we study with correlation functions are studied in PP collisions. And the final state interaction among pairs, triplets, so it's basically imprinted on the correlation function, and is the result of like a dialogue, which takes 1,000 Fermi. Okay, so this dialogue starts at the collision center, but it goes on while the particle travels, meaning that this dialogue takes place in the vacuum, where temperature does not play any role. So, meaning that the interaction, the 2-body, 3-body, 4-body interaction that we have either already studied or we want to study in the future are not influenced by the temperature, because we travel far away. So now the point is more if these many body interaction that we will measure are enough to then describe the cold, compressed neutron stars. This I'm not sure completely about. On the other hand, at the moment, I have not a better idea how to address that. And this is the best idea we have at the moment, to try to address in a clean way many body interactions. I hope I could answer. So yeah, it's BP collision, not lead-lead. Also because in lead-lead, you have, let's say, distances among the pairs or the triplets, which are 5 Fermi, 4 Fermi, and the strong interaction is short range. So you will not see the core of the strong interaction if you collide lead-lead. If you collide PP, the particles are much closer to each other, so you really go down to small distances, which kind of mimic this dense system.
Yes, there are some other questions. I would go to Dominique, who's asking this question that, you see, within the framework you were pedagogically presented. Could you comment what would be the outcome of measurements of hypernuclear interactions foreseen at lower energies, like those in Panda, for example?
Okay, so hypernuclei in general, they obviously are more complex systems because you always have one hyperon, sometimes even 2 hyperons, and many nucleons. And normally, the fact that you have complex system is an advantage, but also a limitation. The advantage is that by looking at different hypernuclei, you can even investigate things like spin-dependent aspect of the interaction, LS coupling, so coupling between spin and angular momentum, and so on and so forth, which you cannot do if you have 2 or 3 particles at LHC. On the other hand, you don't measure in a clean way the 2 and 3 particle interaction. You can only test them because you have at least 10 nucleons, right? I mean, okay, if we take hypertriton, we just have 2 nucleons and 1 lambda, but the problem is that hypertriton is a very large object. It has a radius of 10 Fermi. So also there you don't learn about the short range, okay, not so much. So what I think is that what Panda, for example, will be super in doing is to look at those cascade hypernuclei, which so far, I mean, there is 1 or 2 events in Panda they can produce very abundantly, and also will give us more information about double hyperon, so the hypernuclei with 2 hyperons, which can be 2 lambda or 2 or even 2 psi. So this is something which can help us. So it's complementary with respect to what we do. But it doesn't mean that you can take, it does not mean that one of the 2 research is useless. You need both. So in the end, because we have, let's say, the clean information, but we do not have the more sophisticated system to test all the facets of the interaction. we can give a start, and then the hypernuclei people will take our interaction and see how then it works when you have larger systems. So this is what I think.
Thank you, Laura. Then I see another question which might be interesting, done by Chandra Doy Chatterjee. You see, where does one expect to find the hyperon formation within the neutron star near the core periphery uniformly within the neutron star?
Okay, so this is not an easy question because it depends, as you know very well, on the density. So normally calculations are done such, depending on the interaction, you can predict at which density hyperon will appear. So if you have a equation state, you can say that you need at least a minimal density of so many and so many rho zero. Rho zero is the saturation density of nuclei, normal nuclei. And then you can say, okay, at 3 times rho zero or 4 times rho zero, I will have lambda, sigma, and psi. So in order to know where it will appear, you need to know the density profile, which is something which maybe gravitational wave will help us in understanding, I hope at least. Because obviously only from the mass and radius measurement, you cannot know the gradient of the density, right? Maybe with the precision measurement of gravitational wave, well, while with two neutron stars mergers are going through each other, you can maybe measure the profile or density profile. But in order to know where, you need the density, I think. And so then you can modelize as a function of density. This is what we can help constraining, no more than that.
Thank you very much, Laura. I don't see other questions. So everybody is thanking you. And also we from the Strong 2020 community are thanking you for this inspiring talk, which bring us to the, to particle physics, to the neutron star. Yeah, I see popped up last question. Is it possible to find hypernuclei with bottom quarks? So that's the last question.
So this I actually do not know at all. I know that, what we are trying now is to see whether we can measure interaction with charmed quarks, with charmed hadrons. And then obviously the next stage would be bottom, right? In principle, nothing speaks against, but the effective interaction between a bottom like quark and a bottom quark, a B particle and a nucleus is not known. It might be that the mass, there is such a mass difference that you cannot form stable systems, right? So because all of this is done with masses which are comparable, where binding energy, are much smaller than masses, but partners have a comparable mass. I would say no, let's say, but this is an extremely intuitive answer. What we will do, if possible, is to study the residual interaction for B meson, for example, and nucleons. This is something which is feasible. Producing hypernuclei, nuclei with bottom quarks, may be impossible, but I actually do not know. We have to see.
Thank you. I like this ending. We have to see. So that's thank you for following us in this second lecture. Thank you once again, Laura, and keep in touch. We are organizing now the third lecture, which will probably be in about 1 month by now. If you who are listening to us are having suggestions in the field of strong interaction, just put them down in the comments and we'll try to take them into account. So thank you, everybody, and thank you again, Laura, and thank you to the Frascati team, and see you next time.